Hi, I'm Tom Dick. I'm a math professor and a math advisor for Texas Instruments. This short video is part of the TI-Focus AP Calculus series. Here we're going to use the TI-84 to find areas and slopes related to polar graphs. Let's get started. The first thing we're going to want to do is change our mode from the usual function setting to polar. Once we've made that change in the mode menu, we're ready to go to y equals. What we'll find there is we now have slots for r, the radius, as a function of theta. We're going to use the two curves from question 5 on the BC exam. One of these was simply a constant radius function, r equals 4, which would be a circle of radius 4. The second polar function was 3 plus 2 times the cosine of theta. Now, we're going to graph these. I'm going to use a zoom decimal window. That should be a fairly nice window for these two polar functions. Let's take a look at our graph. And this is exactly the picture that was presented to students on question 5 on the BC exam. Now, if I turn on trace, what you'll see is that we have a readout of theta values as well as x and y coordinates. Right now I'm on that constant radius circle, and if I switch over to the other function, that's the 3 plus 2 cosine theta, advancing the trace cursor, I can see the theta values advancing as well as the change in x and y coordinates. I've switched back over to the other curve, and I do want to show you how to get a readout of the actual polar coordinates as we trace. To do that, we go to Format, and you can see on that top line we have rectangular graphing coordinates. I'm going to change that to polar graph coordinates, and that's what's going to change the look of the trace readouts. So now when we go back to the graph, you can see I have an r and theta readout. Switch over to the other curve, and as I trace along the curve, I can see the readout of r and theta. Okay, now I've advanced the trace cursor to a point of interest to us in this problem. We're asked to find the slope of the tangent line at this point where theta equals pi over 2, which we can see is the point 3, 0 in x and y coordinates. Now that slope is going to be given by dy dx, so I've returned to the calculator screen and we'll use some calculus. Now our functions are given in terms of theta, so to tackle this, we're going to use the chain rule. The y value as a function of theta will be given by r2 times the sine of theta. So r2 times the sine of theta, let's take the derivative with respect to theta at theta equals pi over 2. That's going to give us dy d theta at that point. All right. Once we've entered that, we can calculate it, and we can see that it's very close to -2. Now let's do the same thing for x. X will be given by r2 times cosine theta, and so I'm retrieving r2 from the y variables polar menu, and taking that times cosine theta, and I'm going to calculate the derivative with respect to theta of that function at theta equals pi over 2. And once we've done that, we can see that we get a number very close to -3. And now that we have dy d theta and dx d theta both calculated, I'm going to calculate the ratio of dy d theta over dx d theta, and that will give us our value of dy dx. Now, we can tell that these are very close to integer values, and so we should come up with something like 2/3. Okay. Now, we weren't asked to find the equation of the tangent line, but I would like to go ahead and find that and see if visually our slope of 2/3 makes sense. Going to the Draw menu and see number 6 is DrawF. We can enter an expression for something we'd like to graph on top of the polar graphs. Let's see, we had a slope of 2/3, so I'm going to enter 2x over 3. Our y-intercept was 0, 3, so I'll add on 3. And we draw the tangent line And this looks like nice visual confirmation that our slope made a lot of sense. Now in this problem we were also asked to find the area between the two curves between their intersection points at theta equals pi over 3, which I've jumped to with using the trace, and the second intersection point at 5 pi over 3. So I'm entering theta equals 5 pi over 3 and going to jump to that point using the trace, and we can see visually that makes sense. And this kind of crescent type of region, not really a crescent, this is the area or the region that we want to find the area of. So we're going to return to the use of calculus. I'm going to return to the calculator screen, and the integral that will give us this area is going to be 1/2 times the definite integral. So let's retrieve that from the math menu. There's fn int down there at number 9. And the intersection points were at pi over 3. That will be our lower limit of integration. And the second intersection point was 5 pi over 3. So we'll enter those. And our integrand will be the difference of the squares of the outer curve and the inner curve. So I'm going to retrieve the outer curve, which was R1, from the y variables polar menu. Okay, there's R1. And we will square that. And then we'll subtract the inner curve, which is R2. So I'll go back to the y variables menu, polar, to retrieve R2. And then we'll square that. And then, of course, we'll integrate with respect to theta. Now, because this particular problem was on the non-calculator part of the exam, only the integral expression was asked for in the problem. But we've gone ahead and computed it and gotten the value 21.73. Again, that is the area of this kind of crescent-shaped region between the two polar curves. Well, that concludes this short video. For more resources like these, please see education.ti.com.